Okay, so let's get started. So what we learned last time was the residue theorem, which allowed us to calculate some explicit integrals. So we did one example of this, which was an explicit integral that we actually already knew the answer to because it was something we could do from calculus. But the point of this is that there is now a wealth of methods that are accessible to us that allow us to calculate things that are not within reach of calculus methods. So for the next class, and probably the one after this, also to say for this class and the one after this, I'm gonna teach you some of these methods. There's a different setup for different kinds of integrals, and it's also somewhat interesting in the sense that if, like me, you spend a lot of time teaching calculus, which is probably your future too, you spend an awful lot of time doing these particular, very specific methods to calculate various kinds of integrals, and it might seem like you've got quite a good thing going on, but what you notice somewhat easily is that if you change the situation even slightly, then you can't calculate the integral. You can't explicitly get the integral. So there's hodgepodge of different techniques: integration by parts, use substitution, trigonomic substitution, rational functions. All this different techniques you learn in calculus only work when you're in the very narrow circumstances where you can apply them. And if you have rather natural-looking integrals, then suddenly nothing that you know, nothing that you teach, that you spend weeks teaching calculus students how to do, is of any use. And with this bunch of techniques, suddenly you're wildly expanded in what you can actually calculate. So this is thinking from the perspective of as I said before, of 18th century mathematicians. This was really, really striking and impressive for them. And now, as I teach it now, after many years of teaching calculus, I see that more precisely. I see that more clearly because I realize the limitations of all the things we teach in calculus. Even though we spend a lot of time teaching students how to integrate things, in truth, we can only integrate. we can only win the game when we set things up in a way that we can win the game. If you do a typo when you set up your integration question, it'll look very much like the question you meant to answer. But the fact that you wrote something slightly differently, you'll find out as you try and solve it, you actually can't. That's how fragile calculus methods are. So it's quite an accomplishment to be able to do a much wider class of integrals. So let's start by the following things. So we're going to teach you how to integrate, or I'm going to teach you how to integrate the following kinds of integrals, starting with this kind. So suppose we want to integrate something like this: 0 to 2 pi f of cosine of theta, sine of theta, the theta, where f is, I'm not going to be too specific, f is a nice function, f is analytic in both of its variables here, okay? And we're going to find out it's possible to turn this thing into a holomorphic function in the following way. So let me just say f is very nice. And what we're going to recall is how we formulated the trigonomic sine and cosine. So recall the following. If we do this, if we do e to the ix, recall it is cosine of x plus I sine of x. So therefore, e to the ix, that's plus e to the minus ix over 2. Since sine is odd, this thing will just become cosine of x. And similarly, e to the ix minus e to the minus ix over 2i. This becomes sine of x. And that's how we created the trigonomic sine and cosine. So the complex sine and cosine. Defined like this. So cosine of z is e to the iz plus e to the minus iz over 2, and sine of z equals e to the iz minus e to the minus iz over 2. The stuff we saw already. All right, so we'd like to replace this stuff by something which is going to turn out to be a function which is holomorphic except for some singularities that turn out to be poles. That's going to be our mission. Yeah? So that means somehow rewriting the cosine and the sine using this stuff here. And there's a trick here. There's a trick. So what we're going to do is we're going to say, okay, let's consider the integral around the circle of f of z plus z to the minus 1 over 2 and z minus z to the minus 1 over 2 like this. So I'm going to add some things to this later, but let's just, I want to give you a way to recapture how we do this, how we get it into the right form. And the trick to consider is we're gonna try and replace this thing by the integration around the unit circle of something like this. Okay, something like this. But so let's see what happens if we do that. See how close we get to recovering this expression from this expression. Let's see what happens. So take parameterization. So this thing we're about to work out. So take z of t. Of course, it's going to be equal to e to the it. So z prime of t is equal to I e to the it, like this. Yeah. So you're going to think about this in the following way. So if we now turn this thing into the parameterization, so at the moment it's just dz, and I'm going to put some stuff in later. So then we go 0 to 2 pi. Then we're going to have f of, now z becomes e to the it plus e to the minus it over 2. And then we're going to have e to the it minus e to the minus it over 2i, like this. And then we're going to have whatever we put here, and then z prime of t, which is just I e to the it, like, oops, it like this, and dt. And because this thing just becomes cosine of t, and this thing becomes sine of t, we get close to what we want. We get close to what we want. So we get this thing, oops. We get this thing out of this thing like this. Except that we have this term right here that we do not want. We have this term right here that we do not want. Yeah? So if instead of considering this guy right here, what if we considered this function, 1 over iz, like this? Yeah? And if we did that, then what would happen? Then we'd have 1 over I, and z is e to the it. And then these e to the its would cancel, and then we really would get exactly what we want. Do you see what I mean? Yeah? So you can get the right form from just saying, okay, let me look at this part, and with the memory that I'm going to integrate around the unit circle, and then get the sine and cosine from this stuff here, which is the standard way we define this trigonomic sine and cosine. Then you almost get what you want, except that you have this extra term. So then you go, okay, well, then instead of integrating that guy, I'm going to make a modification so that when I put in the parameterization, then the stuff I don't want actually cancels. Yeah? The stuff I don't want actually cancels. Yeah? All right, so with this trick, what have we learned? We've learned that this guy that we're interested to calculate now becomes this guy here. And if f is nice in the sense that this expression over here turns into something which is holomorphic except for some singularities inside the unit ball, where the singularities are just poles, then this is going to be a nice thing that we can apply the residue theorem to. This thing here is now accessible to us via the residue theorem. Yeah? And it turns out that there's a rather wide class of f such that when you create an expression like this, it is indeed going to be something which is going to be a nice holomorphic function except for finitely many singularities inside the ball. Yeah? So it's the class of f for which this will work. I mean, you can sort of see just algebraically that if you take any kind of polynomial function of both variables, then for sure that's going to be fine, right? Thinking a bit more generally, if you take any kind of rational function of both variables, that's going to be fine. So that we have really a huge class of f for which we can actually do this method. So whenever you see this question and you're asked to integrate around 0 to 2 pi some expression of sines and cosines, it's got to be this. It's got to be turning it into this. Okay? Cool. All right. So let's do an example. This example. Example 1. Let's integrate from 0 to 2 pi 1 over 2 plus cosine of theta squared d theta. And notice that we are indeed out of the realm of stuff that we can apply. This is a nice looking integral, not very complicated, but there's none of our many calculus 2 methods are actually going to help us here. There's no u sub, there's no integration by parts, there's no trigonomic substitution. This is already just completely out of the realm of the toolbox of calculus. Huh? But this is obviously a fairly nice function in terms of f. Yeah, in terms of f. This will indeed be good enough for us. So we are going to do this stuff. So this guy, let's put it over here. We're going to turn it into an integral around the complex numbers, around the unit circle. Okay, so what is our f? Our f is just this guy. So this cosine of theta, we're going to replace by 2 of z plus z to the minus 1 over 2, like this. Yeah? And then we have to add this term over here, 1 over iz, and then now we get this. So this is just the application of this stuff I've done here, that this integral turns into exactly the integral that we want. Are you happy with this? Give me a thumbs up if you see why this turns into this via this. So, let me clean the board and then we'll do it. We were doing this, right? We had 0 to 1 over 2 plus z to the minus 1 over 2, like this, squared, and then 1 over iz dc. That's where we were. Yeah? Cool. So we want to try and make this dz into as nice a form as possible so that we can see what the singularities are inside this thing and then apply the residue theorem. Yeah. So what do I want to do? Let me first of all take out the 1 over I, which is the same as minus I, is 1. I want to multiply top and bottom by z so that I can get rid of the z minus 1. And actually, I want to multiply top and bottom by 2z so I can get rid of the 2 here. So I'm going to have 2z on the top and because I have a z here, I'm going to have 2z squared. Actually, I want 4 because I want to take it inside the square root. So let's put a 4 here. And then I'm going to have a 4z squared outside of this, which I'm going to part. Oh, let me do it in stages. So I'm going to have 4z squared outside like this. And then I'm going to have 2 plus z to the minus 1 over 2 dz, like this. Yeah? Everybody happy? Okay, Laura? Yeah? Okay. So then what? So I'm going to take out the 4. So let's write this out as minus I over 4. 1 over I is minus I. We're integrating around the unit circle S1. And let's take this, oops, I've missed out the squared sign. Let's take this through the square. So we're going to have 4 outside here, which actually, I mean, it's going to cancel. So why do I need it? Let's just get rid of it. Set like this. And, oh, sorry, stupid. We do indeed have the 4, because I'm taking the 4 through this. So then when I write this thing as 2z squared, then I take it through. So then I'm going to have 4z, and then I'm going to have z squared plus 1, like this, dz. And let's put the stuff correctly back. So that's minus I. Yeah, that's correct. So what have I done? I've just written the I as minus I, and I've multiplied the 4 through this thing right here. Yeah? And that's all I've done at this point. And that looks good because now I have a quadratic on the bottom here. Oh, everything should be squared. I keep forgetting this. Now I have a quadratic on the bottom here, so I can actually factor it. Yeah? So z squared plus 4z plus 1 factors, and the factors turn out to be like this. Z minus 2 minus root 3, z minus 2 plus root 3, like this. These are the factors. And these are annoying to write out because they're long, so let z0 be minus 2 minus root 3, and let z1 be minus 2 plus root 3, like this. And then we can rewrite this guy as minus I, the integral around the circle. Actually, now I want to take out the 4. Why not? So minus 4I z over z minus z0 squared z minus z1 squared dz. Yeah? And this is going around the circle, so let's draw a picture. This z0 is minus 2 minus root 3, so it's way out here. It's not inside the circle. Yeah? But this guy, minus 2 plus root 3, actually will be inside the circle. Yeah? So we have z1, it will still be negative. z1 is here, and z2 somewhere over here. We don't care about it. It's outside. Yeah? Cool. So the only singularities of this nice function, which is holomorphic except for some singularities, and the singularities are poles. The only pole we have to care about is at z1. Yeah? The only pole we have to care about is at z1. Cool. All right. To simplify notation as well, let's just write f of z is this function. Okay, this is our nice function. And then by the residue theorem, this thing is minus 4i. And then the residue, or 2 pi I times 2 pi I, the residue at the point z1 of our function f of z. Yeah? So we need to calculate the residue. Yeah, we need to calculate the residue. So need okay, how are we going to do this? What kind of singularity do we have at Z1? Yeah, it's an order 2, right? So we're going to have to use the formula to calculate the residues, right? So tell me about the formula. What did we have to do to actually calculate the residues when we have a pole of order n? In this case, n is 2. What did we have to do? In this case, just one derivative, but derivative of what? Good. So this thing, and there's some other part, there's one other thing you're missing. Factorial is going to be 1. What other thing? Good. Take the limit as z goes to z1, and then we're going to differentiate one time, and we're going to multiply after this entire thing, our function by the pole to the power 2, times the function itself, like this. And we would be factorizing, we would be dividing by n minus 1 factorial, but n is just equal to 2, so that is, n minus 1 is 1, 1 factorial is 1, so we don't have to care about this. So this is the thing we actually have to calculate. Yeah? Cool. All right, so let's take a look at this. So then we have d by dz. When we multiply z minus z1 through this thing, we're just going to have z over z minus z0. Yeah? So it's going to be this thing, z minus z0 squared. And then we just have the quotient rule. So this thing, put everything under the bottom squared. So now it's power 4. Differentiate the top guy, leave this bottom guy alone. Minus, leave the top guy alone. Differentiate the bottom guy. Let's clean that up a little bit. So we can factor out a z minus z0 from everything. So then we're going to have z minus z0. And then we're going to have minus 2z. And then on the bottom, we're going to have z minus z0 to the power 3. And then that has a nice form of minus z0 minus z over z minus z0 to the 3. Yeah? Cool. All right. And then we want the limit of this thing. So limit as z goes to z0 of this expression here in the red box. Oops. No, not Z0, Z1. Okay, so we are going to get minus Z0 minus Z1 here, and then we're going to have Z1 minus Z0 to the power 3. Okay, let's see what this is. So this is Z0 and this is Z1, so Z0 plus Z1 is equal to just minus 4, right? Because the roots will cancel. So minus this will just be 4. So we have 4 on the top right here. And Z1 minus Z0. So Z1 is this thing, and we subtract Z0. This is Z1, we subtract Z0. We are going to have just 2 root 3, like this. Yeah. So we're going to have on the bottom here 2 root 3 to the power 3. So what's that? That is 4. 2 to the 3 is 8. And then 3 to the power 3. So that's 3 squared times root 3. So that's 3 times root 3. And what is that? That is, that's just going to be 1 over 6 root 3, right? We are not done, because what have we done? We've just calculated what the residue is, right? This is just a calculation of the residue. So an easy mistake to make would be to think that this is the answer, but we're not there yet, right? So this is just the residue. Yeah, that's where we started, is equal to this thing. We took the derivative, we took the limit. So let's put in that this is the residue at z1 of our function f. But the actual answer we're looking for is, by the residue theorem, minus 4i times 2 pi times this thing. So the actual answer to our integral, which is no longer here, maybe I just put it back in. I remember it. So the actual answer to the integral, which is equal from 0 to 2 pi of 1 over 2 plus cosine of theta squared d theta, is equal to, so what's this going to be? So I squared is minus 1, so it's going to be 8 pi times this thing, right? So it's going to be 8 pi times 6 over root 3, so that's going to be 4 pi over 3 root 3, and that's the answer. So we can explicitly calculate this real value integral around the circle that is inaccessible by other methods through the complex world, through turning this into a holomorphic function. Okay, cool. And we're later going to learn to integrate indefinite integrals involving a sine or a cosine in a completely different way. So, and the initial idea is completely different as well. So you're going to have to distinguish between this method and the next method rather carefully. So this method uses the fact that we can recover the expressions of sine and cosine from these guys. Again, we do this again. E to the ix plus e to the minus ix over 2. And the idea is that we parameterize around the unit circle, and then this thing becomes our parameterization. So then the cosine expression becomes things like this. Okay, that's the main idea. And once you have that idea, then you try it, and then you see that you get an extra term, and then you just correct out for the extra term by dividing by 1 over iz. Okay, so the two ideas, or maybe the one idea you need to do this kind of thing is we're going to turn it into an integral around the unit circle using this identity, using the fact that z of t equals e to the it is the parameterization we'll use, so that this cosine and sine, in this case cosine, can get turned into this expression. Then just try it and then find out that you need to correct it a little bit. Okay. Okay. So try and do it that way. Don't try and memorize the form. Try and memorize the strategy, and then you'll be more confident about it and more likely to get it right. Okay. Cool. All right. So that is one of the classic types of one of the classic types of real integrals that we can do with the residue theorem. And it's unambiguous. When you see it of this form, it can only be doing it this way. So practice a number of these, and there should be no issue with this. Let's talk about the Cauchy notion of improper integral. So in calculus we teach. So let me say this the proper way, because there's a real term for this. the Koshi principal value. So in calculus, we teach students this. So in calc, we teach that the integral from minus infinity to infinity is equal to the integral from a to infinity f of x dx plus the integral from minus infinity to a f of x dx if both of these things exist. Okay, so we teach this in calculus if both of these things exist, but now we're going to learn a different notion of the integral from minus infinity to infinity. So now we will define integral minus infinity to infinity differently to be equal to the limit as r goes to infinity of minus r to r f of x dx if this limit exists. Okay, so in the calculus definition of this, then we need this limit to exist. So this is the limit as r goes to infinity of the integral from a to r, and this limit to exist is the limit as r goes to infinity of minus r to a f of x. Right? That's what we teach in this section, improper integrals in calc. Yeah, this is a different thing, right? So for every r, this is a meaningful expression, and we want this thing to actually have a limit at infinity. Yeah, are these things different? Can you give an example where these things give you different results? So if there is an example, it's going to be one where we can't take this thing and have it come to some answer, but we can take this thing and have it come to some answer. Yeah. Yeah. So these are different. Can you give me an explicit one? The cube root of x is indeed good enough. Example. F of x is the cube root of x. So this is a nice odd function, exactly as you say. This thing is integrable from minus r to r, but if we try and take the integral from 0 to infinity, then indeed this is not integrable. Yeah? Good. All right, so what I did last time was this integral of minus infinity to infinity, 1 over 1 plus x squared. And I kind of skipped over this without saying it explicitly. I did this by saying, okay, this is the limit as r goes to infinity of minus r to r, 1 over 1 plus x squared dx. Yeah? And then I showed that this thing has a limit, and that was the answer. Yeah? In this case, is our Cauchy principal integral, principal value, whatever it was called, is it different than what we would do if we did the calculus 2 definition? Well, we got the same answer, but also this is perfectly meaningful for this integral because it's convergent, right? Yeah. So if we take this thing, we can break it up from the integral from 0 to r and r to 1 and just consider them completely differently. Yeah. So in this case, it makes no difference, but there are examples where it makes a difference. Yeah. So this definition, I've forgotten the name again, the Koshi or whatever integral, this thing is a more general definition. This allows us to integrate a wider class of functions than we can when we do this. Okay? But every time we can do this, we can certainly do this. Okay? Cool. So with this notion of integrating from minus infinity to infinity, we can actually integrate a fairly wide class of functions. So what we need is the following. So suppose we integrate from minus infinity to infinity, in the Cauchy sense, this thing. Now those are rational functions. What would we need in order for the method we did before to work? So what did we do before? We took a semicircle like this from minus r to r. Look at this. We took the semicircle, right? And then it turned out that when we integrate our function, when this thing is turned into complex numbers, and when we extend it to the complex numbers, when we integrate over the semicircle part, that thing just vanishes as the radius increases. Yeah? And that's why we're able to reduce the complex version around the contour. So consider the integral from around this thing, call this entire contour gamma of r. So consider gamma of r of p of z over q of z. And this guy is an example of such a rational function. It turned out in this case it was working out for us because in the limit, this thing turned into just the limit of this guy over here. But what was the property that allowed that to happen? What would we need in general from the P and the Q? So let's write it out. So what is this? This is the integral from minus r to r of this thing. This is the guy we want. This is now just a real integral when we integrate over this part of the real line, right? And then it's this thing. Gamma of r, take away this thing. This is semicircle part. Yeah? And we want this thing to vanish. Yeah? So we're not going to use any... Go ahead. Yeah? But is that enough? So if we just take... So we didn't do anything to do with cancellation or anything. We just took the absolute value of the expression inside, right? So then the length of this guy right here is half the semicircle. So it's just pi times r. That's the length. Yeah? Yeah? So when we take absolute value inside, we're integrating over something which has got pi times r length. Yeah? And indeed, we want this function to get smaller as z goes further and further outwards, right? As the radius of the semicircle increases. But is that enough? Is that enough that it gets smaller? Are you saying that we just need that P of z over Q of z goes to 0 as z goes to infinity? Will that be good enough? Okay. So if it goes to 0, like what rate would you like? So let's try and estimate this thing in the green box. So thing in the green box is less than the length of the curve, which is just pi times r. And then the supremum over this set right here of the absolute value of P of z over Q of z. Yeah? Yeah? So what do we require? So what weight will it have to go in that case? So remember, it's a rational function. Yeah? So how far? What's the rate at which it goes to 0? So what I'm trying to say is, can it go, for example, to 0 like 1 over capital R to the 3 over 2? Is that possible? Yep, because the rate at which it decays has to be an integer, right? It has to be an integer rate of decay because the leading order term of this guy is z to something, the leading order term of this guy is z to something else, say z to the n, and this guy would be z to the m, yeah? So we'd need m to be bigger than n, yeah? And then the decay of this thing would be the absolute value of z times n minus n, yeah? Let me say that in the language of maths. So if P of z is equal to whatever coefficient, say a m z to the m, blah, 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 and then Q of z is equal to, let's call them b n z to the n, blah, blah, blah. Then n has to be bigger than m in order for this thing to go to 0. Yeah? And the absolute value of P of z over Q of z is, for very large for very large z, we don't care about any of the other terms. They're insignificant. Yeah? So this will be like the absolute value of am over bm. We also don't care too much about that. It's just a number. And then it'll be absolute value of z to the m minus n. Yeah? And m minus n, let me put an example for very large z. And let me even put a 2 here just to make sure it's true. So for very large z, this will be true. And m minus n has to be an integer. Yeah? Has to be an integer. And that integer can't just be 1. Sorry, it can't just be minus 1. Because if it was just minus 1, then we'd have something here, which is like r to the minus 1 times r. Do you see what I mean? Yeah? Yeah? So then this integer, therefore, at least has to be equal to minus 2. At least has to be equal to minus 2 in order for this thing to have a hope to work. And then from this, we backward engineer what condition we need for this to work. We need that the degree of P to be less than the degree of Q by 2. Maybe better to say that. Degree of Q is degree of P plus at least 2. Yeah? So need degree of Q to be bigger than equal to the degree of P plus 2. Yeah? Yeah? Cool. However, if we do have that, then this inequality I've done here does indeed give us that for very large, as we let r tend to infinity, this thing, sure enough, will go to 0, because this is for sure true, right? If we have some polynomial, then if we take the radius large enough, maybe I'll give you some details of this just in case it's not completely clear. Right? P of z equals am z to the m plus am minus 1 z to the m minus 1, and then so on. Then we can write this as a m z to the m, and then let's factor z to the m from everything else. We have plus like 1, and then let's not do it this way. Let's write it this way. Let's factor out a zm right at the front. So this is zm, and then we have am, and then am minus 1, and then we're going to have z to the minus 1, and then am minus 2, z to the minus 2, and so on. Yeah? So for very large z, this becomes more and more just like z to the m times am, because all of these terms here are just going down to 0. Yeah? And we do the same trick for q. So q of z equals z to the n, and I called it bn plus bn minus 1 z to the minus 1 plus a whole bunch of terms that go down to 0. So then when we consider this p of z over q of z absolute value, then it is like the absolute value of m minus n, and then these expressions here. So the absolute value of am plus am minus 1 z to the minus 1 plus dot 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 over bn plus bn minus 1 z to the minus 1 plus dot dot dot, like this, right? Like this. Then what? Then for large enough z, we know that this guy will be less than, say, twice the absolute value of am. So just looking at the top, because all these other terms get negligible as the modulus of z gets bigger and bigger, we can guarantee that the top part of this quotient is less than twice the absolute value of am, so long as absolute value of z is large enough. Do you see what I mean? Yeah? Give me thumbs up if you do. Okay. And we can also guarantee that this bottom part is at least half of this guy, because all the other coefficients get arbitrarily small. It's at least half of this guy. Yeah, it doesn't matter what this bn minus 1 is and all the other terms. We can just guarantee that I put it over here. Look at this. So absolute value of bn plus bn minus 1, z to the minus 1, blah, 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 all these other guys by the triangle inequality is bn minus the absolute value of all these guys, blah, 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 blah. And we can make this arbitrarily small as z gets big. So then this is bigger than or equal to bn over 2. Yeah? Okay, so we have that the top half is less than twice the absolute value of am, and the bottom half is at least half of bn over 2. Yeah? For all large enough c. So then this entire expression here is less than, oops, it's less than mod z to the m minus n, and then twice am over half absolute value of bn, so then it's less than 4 mod z m minus n, and then this number here, am over mod bm. So better to put a 4. We can have any number bigger than 1, but the way I chose it, we have a 4. So now we completely have this for sure. Yeah? For all large enough radius, this estimate is correct. Yeah? And our assumption is that the degree of q, which is this n, is the degree of p, which is this m plus at least 2. So then this expression here is at least minus 2, and that's what we need. Yeah, that's what we need in order to just take the absolute value of this thing right here, yeah? And then we'll have some particular constant, this constant, mod z to some minus something, which is at least minus 2. Yeah, which will definitely kill the r. All right, so we should have been, everything should be completely like nailed down with certainty at this point. Are you with me? Are you with me? Yeah, okay, perfect. So that means whenever we have some expression like this, we can do exactly the same method. We can just create a semicircle and then show that the things we have on the degree of p and q mean that the upper part of the semicircle just go to 0. However, if you see this in an exam, in a prelim exam, I want you to show it. I don't want you to just state it. I want you to show it. I want you to do these estimates because, again, it's about showing you know why this works rather than just carrying it out. Okay, so you will lose marks unless you show this. And I claim that this should be fairly straightforward. If you go through this argument by yourself, these are straightforward estimates. These are simple things. It should be a straightforward thing that for very large c, then polynomials are basically like their leading order term. Yeah? And that's basically what we've done here. Yeah? We've just been a little bit more rigorous about this fact. We've used the language of maths to specify what we mean by this fact, and then it just falls out. Okay, now we're going to learn the following stuff. So sometimes we're going to be interested to do integrals of this form. We're going to have integral from minus infinity to infinity, some rational function, p of x over q of x. And now we're going to have something like this, e to the I times x dx, like this. And what's the point of this? Well, the point of this is that e to the ix we can write as cosine of x plus I sine of x, like this. So that if we calculate this, then this is the same as the integral from minus infinity to infinity p of x over q of x cosine of x dx plus the integral from minus infinity to infinity p of x over q of x I sine of x. So we can actually calculate these brilliant integrals p of x over q of x times a cosine or times a sine, because when we evaluate this, then the real part will be this guy and the imaginary part will be this guy. Okay, so it's another way to integrate something that involves a sine and a cosine, but now it's very different. Now it's very different. So if you see this and you see some function and then times cosine, do not try and write the cosine as the trigonomic function. Try and put it in its form of the complex trig. You instead have to think of this as just being the real part of this guy or the imaginary part of this guy. If you try and do it by recreating the cosine with the trig function, it just won't work. Okay, so you have to differentiate these two methods to deal with some new type of integral involving a sine and a cosine. Okay, so the previous one works when we have a unit circle. This improper integral of type 1 is from doing this. And there's a interesting wrinkle in this, in that we can actually deal with a wider class of p and q. So this thing, this e to the ix is just a unit vector, right, around the complex numbers for every single x. So as you can imagine, if you take the absolute value, well, as hopefully you know, you take the absolute value, it just becomes p of x over q of x. So if we do a semicircle thing, like this, then if the degree of the q is the degree of p plus at least 2, then taking the absolute value of this thing means that on the semicircle it will vanish and we'll be able to extract the integral. Okay? Yeah? You see what I mean? Give me some feedback, people. Give me a thumbs up or something I can see. Laura, are you okay? Okay, good. So we can use the old method if we happen to have that degree of q is at least the degree of p plus 2. Yeah? But we can actually do this when the degree of q is just 1 bigger than the degree of p, because we can use the special properties of this kind of situation. Yeah? So if you see this, there's a good chance they're not going to make it easy for you. They will have this not be where the degree of p is degree of q minus 2 or more. It'll just be that the degree of q is just 1 more degree of p. So if you try and do this, it just won't work. It won't cancel for the reasons we just discussed. Okay? So it's another reason why you need to understand this and not memorize procedures, because it looks kind of like it's accessible via this, but it doesn't work. So I'll show you the different kind of procedure we need, the different kind of contour we need to calculate something like this. So note, let me just state this as where degree of q is at least degree of p plus 1. And that's all we're going to need for this thing to actually converge. Okay. But not with this contour. This contour is no good. So instead we're going to use the following contour. We're going to go from minus r to r, and then take r go to infinity, of course. But we're going to create a rectangle where we go up like this, and then go along, and then go down. So the height of this rectangle is going to be capital Y. So then what is this thing here? This is going to be r plus I times capital Y, and this will be r minus r plus I times Y. okay? And we're going to do this in stages. We're going to take the limit as, well, you're going to see the order, but we're going to take the limit as y goes to infinity and then as r goes to infinity afterwards. And you need to do it in this way. So let gamma of ry be this contour, be this particular contour, okay? And I'm going to break it up into pieces, and let's let gamma 1 y be this left-hand side. I wanna have better notation. So, and put it here. So gamma y is this contour. And then we'll label the sides. So this is the guy 2, or gamma 2 y, and this is gamma 3 y, like this. Okay? And what we'd like to do is to show that on gamma 1, gamma 2, gamma 3, everything vanishes, yeah? As r or y goes to infinity. And that's what we're going to show, because if we can do that, then all that will be left will be the singularities in the upper half plane. Yeah? And this is a rational function, so it has at most finite many singularities in the upper half plane, and we'll just calculate it. Yeah? Yeah? Cool. So that is what we want. I should also add a kind of caveat that implicitly, even though I haven't said it, we're assuming that we don't have any singularities on the real line, because if we do, then we can't apply the residue theorem. We need to do the contour where the function's actually analytic. Later, we're going to learn to deal with the situation when there are singularities in the real line, but right now we don't know how to do it. Okay? So that's another condition we need on P and Q. So where Q, well, let's write it this way, where there are no poles of P of z over Q of z on R. All right, so let's start by trying to estimate gamma 1. It's going to be the same for gamma 3, but let's see how it goes. So if we turn this into a complex integral, and then we are integrating gamma 1 of y, and it's P of z over Q of z, and then e to the iz dz. We just put it in the parameterization, right? So let z1, actually, why not? I need to call it 1. Let's just call it z of t. Be the thing that parameterizes this curve. So we start at r, we end up at r plus iy, so the natural choice is r plus I times t for t between 0 and y. That gives us the parameterization that we want, yeah? And then let's see what happens. So if we differentiate this guy, what do we get? We just get I, that's simple. So then let's rewrite this guy with our parameterization. So we're going from 0 to y, and then we have P of z of t over Q of z of t. And what do we have here? We have E times I R plus I times t, like this. And then we just have I dt, like this. Okay, let's take out the I. We don't care about it. 0 to y. Then P of z of t of Q of z of t. And then what happens here? Then we're going to have e to the minus t, and then plus e to the IR dt. Okay, let's see what we have to care about. So we're going to take the absolute, actually let's put the I inside, so we're going to take the absolute value signs. So we're going to take the absolute value signs, right? So we're integrating along here, yeah? So the distance of z away from 0 is at least r. It's at least r, yeah? It's at least r as we go from here to here. And we know from the same argument as before that for large z, then this P of z over Q of z is going to be bounded by some constant times 1 over r, absolute value of r. But the same thing we did before. Let's put it up here. So absolute value of p of z over q of z is less than some particular constant. I don't care what it is. Z to the minus 1 for all z bigger than something. Absolute value of z bigger, whatever, capital A. Yeah, there exist these constants c and capital A such that this is true by exactly the same argument we did before. Yeah? Are you happy with that? Yeah? Cool. So this guy here, if we take the absolute value signs throughout this, let's do it here. So call this thing star. So then star is less than, let's take the absolute value signs, 0 to y, then the absolute value of this thing like this. This is just a unit vector, right? The absolute value is 1, so then it's just equal to e to the it dt. But this thing, as we just argued, since we're at least distance r away from 0, and r is getting bigger and bigger, we can assume r is at least bigger than capital A. So then this estimate here means that this guy will be less than 1 over r. This guy will be less than 1 over r. Do you see what I mean? Yeah? So then this entire thing is less than constant r to the minus 1. This constant c just depends on our polynomials. We don't care about it. And then it's just the integral from 0 to y, e to the minus t dt, and that's an integral we can calculate, of course. So that's c r to the minus 1, and the derivative is minus e to the minus t, so 0 minus e to the minus t, and then this thing is just less than r to the minus 1, because this thing is just 1 minus e to the minus y, and that thing is less than 1. So we have this estimate like this. Yeah? Okay, cool. So this is independent of y. This is independent of y. The y is not important anymore. And we know that this thing is less than r to the minus 1. So that should be okay. That part should be okay as we let r goes to infinity. Yeah? Cool. So now we want to deal with this top part. So I'm going to have to erase everything and deal with the top part. So let's draw the picture. We go from minus r to r. This guy was r plus iy, and this is minus r plus iy. And this is what we called gamma 2 of, I don't know which way around we put it. I think we put, I don't know, did we put ry like this? Anyway, this is gamma 2 of ry. This part right here, and this was gamma 1 of ry, and this was gamma 3 of ry. So gamma 1 and gamma 3 we are happy with. Now we want to think about gamma 2. And our function is this thing. So it is e to the, or it's p of z over q of z, first of all. And then it is e to the iz dz. And we want a parameterization of this part. So what we're going to take z of t. The natural choice is to just do t plus iy, where t is between minus r and r. Yeah, that thing will be fine. Yeah, that thing will exactly parameterize this part right here that we are looking for. We're trying to do this. Yeah? Cool. All right, so this parameterization, when we differentiate it, rather nice. It's just 1. So then this thing is the integral from minus r to r. And we have p of z of t over q of z of t, like this. And then we have e to the I, and then we put in the specific form of parameterization, t plus I of y, like this. Yeah? And then the dz is just dt because z prime is just 1. All right, so if we take the absolute values of this thing, take the absolute value inside, so it's minus r to r, we are, take again the absolute value of this, like this, and what do we get from this thing? We have e to the it and then e to the minus y dy, like this. Yeah? Cool. And then we are in pretty good shape because this e to the minus y, this is t, this e to the minus y, we can just pull it directly out. This thing, that's the absolute value here, this thing is unit vector, that's not going to change anything. So then what is this less than equal to? This is less than equal to integral from minus r to r. For the same reasons before, since the distance of z away from 0 is at least y along the top of this guy, so this guy is less than a constant over y itself, like this. Yeah? Take the absolute value of this thing, this guy is just unit vector, so then this is just e to the minus y. And then this is dt. So these things all together are just constants. So then this is just less than equal to c e to the minus y over y, and then just times 2r. Yeah? And in terms of controlling it as y increases, we have more than we need, right? So we don't even need this 1 over y because e to the minus y is going to 0 very, very fast, yeah, as y increases. However, r is obviously blowing up. So we have to take our limits in the right order. Yeah? The last thing we controlled, it was less than a constant times 1 over r. Yeah? This thing is less than this expression, which is good if we take y going to infinity, but not good at all if we take r going to infinity. Yeah? So what we're going to do, let me underline this, is the following. So we can explicitly calculate this thing. We can explicitly calculate around this contour r of y. Yeah? And this is our function, p of z over q of z, and then e to the I times z dz, right? And this is just a rectangle. It'll have singularities inside. We can explicitly calculate this for every choice of r and y. Yeah? Cool. And if we take some large r and then let y go off to infinity, yeah, then we're going to have some consistent limit because there are just going to be finitely many singularities of this expression in the upper half plane, right? So the limit as y goes to infinity of this rectangle for sure exists, yeah? For any r which doesn't intersect any of the singularities. In fact, since the singularities in the upper half plane are finite, let's just take r to be big enough so that this thing is wide enough to contain all of them, which we can do. Yeah? And then we let y go to infinity, and we do indeed get a limit. So we're allowed to do this. We can take the limit as y goes to infinity, and that makes sense. Yeah? And we're also, after doing that, we're going to take the limit as r goes to infinity. Yeah? And if we take the limit as y goes to infinity, then this part of the integral is going to go down to 0. We're not going to notice it. Yeah? And you notice in the last estimate we had, it didn't care about y. It was just a constant over r. So the sides don't care how big y is. The sides don't care how big y is. Yeah? So indeed, we can also take the limit as r goes to infinity and have that thing vanishes. That thing will also vanish. Yeah? So all we'll have left from doing the limits in this order is just the limit as r goes to infinity of minus r to r of just the real part of this thing, just this side here, where stuff doesn't vanish. Yeah? Cool. And as a practical matter, because we know that this thing isn't going to change after we create a rectangle that contains all of our singularities in the upper half plane, that's all we have to do. That's all we have to do. Because the answer is fixed. You know, once we have a rectangle for some large y, if this contains all of our singularities, then as we let y go to infinity, that integral is not changing. And as we let r go to infinity, that integral is also not changing. Yeah? Cool. So all we need to do is simply find the r and the y that contain all of these singularities. Yeah? And then calculate this expression here, and that thing will be this thing. It will be this thing. Which is another pretty remarkable thing about this thing. This is, this is a very strange fact, but it's true. So yeah, this allows us to explicitly calculate integrals of this form, and yeah, we don't have time to do one. So let me see if I even wrote one down. So next time we're going to do this, for example. We're going to do this. This thing is, again, a fairly innocuous looking integral. It looks fairly harmless, but give this to your Calc 2 students and they will struggle for a long time. They won't be able to do it. They won't be able to do it because of our hodgepodge of different methods that we learn in Calc 2 can't do this. Nothing helps. Even though it looks like something should work, it just doesn't. However, it does fall into this big machine because the degree of the rational function is -1. The degree on the top is 1 less than the degree on the bottom. And we can find this part as the imaginary part of this guy. Yeah? So this thing is accessible. So this explicit integral will come down to, well, notice that this is a symmetric expression, so this is the same as a half of the integral minus infinity to infinity. This thing will come down to just calculating the residues of the holomorphic function we create out of this at its singularities. And there'll just be just a couple of singularities, because on the bottom we see that this is just a nice quadratic. Yeah? Cool. So this won't be particularly difficult. This won't be particularly difficult. Cool. All right, so we'll do this next time. Have a great weekend, people. I will see you all on Tuesday.